So I'm very pleased today to introduce Pablo Rodriguez-Fernandez. Many of you know him well, but Pablo studied industrial engineering in Madrid at the Polytechnic University of Madrid. And then he got a master's degree in mechanical engineering from Drexel University in the US. And then much to our delight, he switched to plasma physics and did his PhD here at MIT, working under Ann White's tutelage. And he worked on transport model validation using CMOD and DIII-D data. He graduated in 2019, had a 2-year postdoc, and then was promoted to research scientist. And he's working on predictive transport modeling, validation, optimization, in particular applied to predict performance in SPARC, but also looking at JET, ASICS upgrade, and DIII-D experimental results. And a fun fact that some of you might not know, in 2021, Pablo was listed by Forbes magazine as one of their 30 under 30 up and coming scientists. So we can concur that he's definitely up and coming. So Pablo, take it away. I'll let you introduce your own talk.
All right. Thank you very much, Earl, for the introduction. And I was really looking forward to giving this talk, really, because this is the first time that I'm taking this
Pablo, you may want to stand near one of these microphones, because I think otherwise people won't hear you.
I see. All right. Well, let's move around.
Yeah.
Yes. So I was looking forward to giving this talk because this is the first time that I'm putting together a piece story and comprehensive story of what Nathan and I have been up to for the last 1.5 years, developing surrogate-based optimization techniques to have high-fidelity predictions of performance. You may have seen part of this talk maybe in a SPARC meeting, JET meeting, but this is the first time that we have put everything together. And let me start by thanking Jeff Candy and Emily Belli from General Atomics for the development of CGYRO, which is really the basis of this work that we're going to see in a minute. So let me start by saying that this is a very exciting moment for core transport research. For many decades, we have run tokamak experiments dating back to the 50s and 60s. And since the very beginning of tokamak research, the scientists have seen clear evidence of anomalous transport, meaning that the energy and particle transport levels that you get from the experiment are much higher than what you would expect from simple collisional theory in classical transport. And there is clear evidence of that since the 70s even. This is data from Agathor A, showing a clear gap between the experimental energy confinement time and the prediction by neoclassical theory. Not only that there is a gap, but also the trend is completely opposite, increasing confinement with density. Also, since the very beginning, we have seen correlation of that confinement time and that anomalous transport with fluctuations, with turbulence. We have seen that as fluctuations in the plasma that we can measure decrease, also the anomalous transport decreases and the energy confinement increases. And we have evidence of that, as I said, from the 70s and 80s. And this is not like just a very small, uninteresting plasma physics question of what is anomalous transport, what is turbulent transport. This has also big implications for the realization of fusion energy. Since the 80s, the community has known that if we didn't have anomalous transport in tokamaks, machines like JET and TFTR would be already initial machines, and we probably would have fusion in our grids nowadays. So this is a very important issue in the community to try to understand, model, and predict turbulence and anomalous transport. And the community has been doing that. Basically, since the 80s, we have been developing the nonlinear gyrokinetic theory, an elegant framework to study turbulence and to study transport tokamaks. And almost simultaneously started an effort to validate those predictions, those codes, those simulations, compare them to measurements of turbulence, compare them to measurements of profiles. A few years later, I would say in the 2000s, really this started the development of reduced models. Basically taking the insights and what we have learned from gyrokinetic theory and use that to create models that can run fast so that we can use them with a transport modeling framework to predict profiles in future machines like ITER. And we have been doing those predictions with reduced models for a while already, for ITER, for SPARC, for demo. The community worldwide is using those reduced transport models. And why do I say that we're at an exciting time in core transport research? It's because now I think we're starting a new era, the era of using directly high-fidelity gyrokinetic simulations to inform the design of fusion machines, to optimize their operation, to optimize how we are designing these machines. In 2022, there have been a few developments that encourage this view. The one that I will be talking about here is the first ever prediction of burning plasma with high-fidelity gyrokinetic theory, with high-fidelity gyrokinetic simulations, nonlinear simulations, or SPARC. Also, colleagues at the Max Planck used also nonlinear gyrokinetic simulations gene to predict self-consistently profiles in ASDEX upgrade. And I'm aware that they are also working towards ITER predictions. So the fact that we are starting to do this now is not really something isolated. This has really been thanks to the decades of development in gyrokinetic theory, in code development, supercomputers, experimental validation. There are too many to cite here. But I would like to mention 3 papers, 3 studies that have worked towards bringing turbulence codes to transport timescales, meaning use turbulence codes to predict profiles and performance. That's Candice, Barnes, and Parker's work. Those were the first ones to use numerical methods to accomplish gyrokinetic simulations of profiles. And 2022 was also very exciting from the gyrofluid perspective. Particular colleagues at the Max Planck used TGLF, gyrofluid model, quasi-linear, full radius simulations to predict ASDEX, and shown that it does better than using empirical models, even if those empirical models have been fitted to ASDEX data. And also colleagues at Princeton have been developing the GX flexible fidelity code, moment-based gyrokinetic code, that is showing a lot of potential, even though it's in its early stages, but it's really powerful. So with this introduction, this motivation of why this is an exciting time for transport modeling research, this is the outline of my talk here. I'm going to talk about how we model core turbulence and how we use core turbulence simulations to predict performance with flux-driven simulations. I'm going to talk about what portals is, and I'm going to talk about 4 applications of this framework to study SPARC, ITER predictions, and study validation of gyrokinetics in JET and DIII-D. And what we're going to finish with talking about advantages and challenges of this framework and what the future holds for us. So the ultimate goal of core transport research is really to answer this question: how hot the core of the plasma gets when we deliver power into it. So we have here a tokamak, you put power in, and we want to know how much fusion power you produce. And really, how much fusion power you produce means how hot you get the plasma in the center. Basically, what gradients you achieve in the plasma. That's going to determine how much fusion you get. And the way to do that, the way to model plasmas, ideally, would be to say, well, I'm going to evolve the full distribution function of all your species with some kind of like Fokker-Planck equation, kinetic equation with some collisions and some sources. But that's way too expensive to do by many orders of magnitude. So back in the 70s, 80s, and all these decades, very smart people started developing a very elegant theory that removes one dimension in that distribution function. Assumes that the past gyro motion of particle can be simplified by having a ring of charge that just follow the motion of a guiding center. That's gyrokinetics. Instead of solving 3D velocity space, you have a 2D velocity space. That is built up with some kind of like gyrokinetic framework. And that's what we would call the global full-F gyrokinetics. Full-F in the sense that get the solution of this equation, you're actually evolving the full distribution function. But this is still too expensive. So what else can we do to make simulations feasible in the core of tokamaks? One assumption that you can make is to take advantage of the separation of scales between turbulence and transport. We know that turbulence works in a micro scale, like small scales, a microsecond kind of time scale. And transport, macroscopic evolution of the plasma, works at a second and a meter, kind of like temporal and spatial scales. So you could take advantage of that in a delta F framework. That's delta F gyrokinetics. The idea here is that you only evolve the fluctuating part of the distribution function. You evolve turbulence with fixed background. You let it saturate, and then you use the information about the heat flux that you get out of that simulation to evolve the macroscopic plasma. And if you have some kind of numerical method or PDE solver, you could move the macroscopic plasma to a next step where you would run again simulation of turbulence, and you start doing that in steps. And it can be shown that the speed up that you get by doing that can be orders of magnitude, and even more when you go to machines like ITER with small raw star, with small ion gyro radius compared to the machine size. So these are a big speed up already. But we can do more things to simplify the system. And one of them is assume locality. We are only interested in structures that are small enough, the ion gyro radius. We can actually, instead of running simulation of the whole plasma globally, we could run small local regions, the flux tube approximation. That's the local delta F gyrokinetics. And it can be shown that at small raw star, meaning as you go to burning plasmas in SPARC and ITER, the local simulations converge to the global solution, because you start having gyro-bone scaling of turbulence, very, very small structures. And as long as you are not studying things like avalanches or internal transport barriers, the local delta F approximation works pretty well. But the community has not stopped there, because this is typically had been already quite expensive. People have been developing gyrofluid frameworks, meaning instead of solving for the distribution function, you take moments of it and you solve a system of fluid equations. That's what codes like DIII-D or GX do. And the idea with those codes is that you have a smart way of close the system to retain kinetic effects. And you want to reproduce the instabilities, this just flow rate, real frequency instabilities in wave number space from the gyrokinetic simulations with just the gyrofluid system. And the last approximation, that's what people use to model really predict performance in devices, is the quasi-linear assumption. So solving for the nonlinear evolution of turbulence, even gyrofluid turbulence, is quite expensive. So one approach is to say, well, I'm going to only solve for the linear characteristics, eigenmodes, growth rates, real frequencies, and I'm going to find a way to relate those linear features to the fluxes that I need for the transport evolution. And you do that by basically feeding functional forms to things like the saturated amplitude of, in this case, the potential fluctuations, kind of assuming a mixing length kind of estimate. And that's how codes like TGLF or qualities work. And these codes can run very fast in the 5 to 10 CPU seconds. So you can couple that to a transport solver. And what we want to do here is basically go up in that ladder. We want to avoid having to make those approximations about quasi-linearity and fluids. And we want to try to solve directly the local delta F gyrokinetic framework. And that's what we have been working on. So why hasn't been done already? Like why people are not using directly gyrokinetics to predict profiles? And the reason is because you need a lot of evaluations of your code to get convergence. And if your code is very expensive to run, that becomes very, very computationally intensive. So to couple the macroscopic evolution with a turbulence code, you basically need a numerical method that couples both of them. That numerical method can be something like Newton method. I'm showing here an example of the solution with DGyro that uses Newton methods. This is, I'm plotting here as an example of the residual. With residual, I mean the difference between transport, between fluxes between your sources, your macroscopic power flows, and your turbulence. At the beginning of the simulation, the two are very different. You have a high residual. And with a numerical method, the idea is that you would evolve the gradients until you get them to be equal to each other, that you would say, okay, that's the steady state, right? That typically requires hundreds of evaluations of your code. So if you have a high fidelity gyrokinetics code that takes 100,000 CPU hours, and you have to run it for hundreds of time to get to a steady state. That's when things become complicated. There are other methods, PDE, time evolution, that's used in the remodeling frameworks. Basically, you just evolve the system until you get to steady state. And that also requires hundreds or thousands of evaluations. And there are other methods that also require a lot of them. And that's because it's common to see profile predictions with reduced models that run in seconds in CPU instead of seeing gyrokinetics. And what we are working towards is to actually try to say, well, I want to keep the fidelity of nonlinear gyrokinetics, but I'm going to try to find a way to get steady state with the lowest number of code evaluations. Because then even if each evaluation is expensive, you can do it in maybe 10 or 20. Maybe you can do full nonlinear predictions of profiles with gyrokinetics. So how are we doing that? So to understand what we are doing, we have to go back to 1950 in South Africa. Actually, we have to look at the birth of geostatistics. So by then, there was an engineer, Daniel Craig, that developed a method to predict gold deposits between sample locations to optimize mining operations. So imagine that you have some map and you have sampled some locations and you have measured the density of gold in those locations. You want to find a way to interpolate in between so that informs you where to evaluate next, where to go and mine, and have high probability of finding gold there. The fundamentals of this is that you can only evaluate at a few sample points because it's expensive to go and mine everywhere. We don't know what the underlying function is. We don't know what was the rock dynamics or how the gold got there. But we know that there exists this correlation, meaning that if you find out a place that you have a lot of gold, it's likely that near that place you have also high density of gold. And that's the basis of the design and analysis of experiments, data, and Bayesian optimization. With some subtleties, but that's basically the idea. You use some interpolation method that lets you sample the space more efficiently. And believe it or not, the way I see gyrokinetic flux matching is like a gold mining exercise. Want to find where the gold is, these are gradients, your plasma. You want to find the situation where the transport flux is equal to your sources, your target flux, and you want to get there, sampling the space at a few locations, as few locations as possible, because each of them require 100,000 CPU hours to evaluate with a gyrokinetic code. So, want to answer the question: what expensive simulation to run next that gets you closer to the steady state? That's what we do in Portals. We have developed this framework to do flux matching using this idea of surrogate-based optimization. And the idea is, well, I'll show you here an example of a function. We don't know the function a priori, but we want to minimize it. We want to find the x that gives you the minimum value of that function. And the way you start is by sampling the space. You take a few simulations, a few selection of x, can be your gradient. You run that simulation and you feed a surrogate model to that. See here, you interpolate in between. The surrogate model can be a Gaussian process or can be a polynomial or whatever you want, or a neural net. A surrogate for your underlying function. And once you have that, you can optimize it and find the optimum, the minimum of that surrogate function. But of course, that's not the minimum of the real function. But then you can take that point and evaluate it again with your framework and add it to the training set. So that little by little, you start adding points to your surrogate model and getting more accurate as you approach the minimum of the real problem. So that's what we do with our flux matching problem. When you think about it, it's very similar. It's kind of like an extension of linear optimization. Linear optimization, imagine that you start here. You could calculate the local derivative. If you're using some kind of gradient descent method or something like that, you evaluate the central differences, your derivative locally, and you feed a linear function, and you use it to move to the next step. Here we're doing something similar, but instead of locally, we're doing globally. We're feeding a global method, a global surrogate model, and use it to help us move in the input space. So there are a few challenges in applying this to flux matching. And one of them is the high dimensionality. So when we have standard problem, for example, we want to predict electron temperature, ion temperature, electron density at some number of radial locations with these CGR simulations that take a long time to run. That means that our problem has 3 times NR, 3 parameters of the gradients, and want to minimize 3 times NR fluxes at each location. In standard surrogate-based optimization, that would mean that you will have to define a flux at one location as a function of all your 3 parameters, right? Because if you're calculating the flux in the core, even if you're running a local simulation, that's going to be affected by what's the gradient at the edge. But the gradient at the edge, if you integrate it, is going to give you a different value of the temperature in the core. So things like collisionality and ratios are going to change. So QE at 12.2 is going to depend on LTE at 0.4. So how do we manage this? Because this means that if we're using, for example, 5 radial points, that means that we have to fit a 15 dimensions function. And actually, we have to do that for every flux. So that would be very expensive. We would need a lot of samples to really fit that problem. So what we do is to exploit the flux nature of our simulations, all right? The flux tube nature of our simulations. So we know that the heat flux in the core is affected by the gradients at the edge, but how they are affected? They're affected because they are integrated into some value of temperature in that position, because it's locally with your simulation that you're running. So you could define just 6 variables, and some of those variables are defined as the integral radius of the rest of the 3 parameters. We could also make the lives of our surrogates easier if we tell them that actually what matters in turbulence simulations is things like the temperature ratios, collisionality, and the ion sound speed, for example. And we actually fit it to Jeroboam units to make it even more straightforward. And that's what we have done. We have our model, that is this box here, that takes the 15, let's say, 3 parameters. It outputs the fluxes in real units, but the surrogates are only fitted to 6 dimensions, to six variables, because of the local nature of our simulations. That makes things much easier to handle. And actually doing it this way, what we are doing is really decoupling the root finding method and the surrogate optimization and the surrogate fitting. It means that we can include high complexity of targets, of sources and sinks in our macroscopic transport evolution. We can include energy exchange, both classical and turbulent exchange. We can include alpha heating to the electrons, to the ions. We can include impurity radiation, Bremsstrahlung, light radiation, synchrotron, and we're also working on implementing auxiliary heating as well. You could add a lot of complexity to this because the optimization, the root finding, occurs for the surrogate, which is very fast to evaluate. So you could add complexity. And just a last note before I go to applications is that we have implemented this workflow in the PyTorch environment. So PyTorch is a machine learning framework developed by Meta Research, former Facebook. And we're in close contact now with the adaptive experimentation team, because they have developed a few libraries that are very useful for what we are doing here, OTorch and GPITorch. And we're exploiting 2 things in those libraries. One of them is automatic differentiation. What is automatic differentiation? Automatic differentiation means that you could build a complex system, a complex set of operations that you make to your 3 parameters. And those operations are stored in memory so that you could call the derivative of your output very easily and exact, not using a numerical method. So if we can go back, we have this very complicated model where we are integrating radius, pre-processing, post-processing. All this is done such as that we can call the derivative of the flux with respect to any of the gradients just with 1 line of code in an exact way. We're also using Gaussian processes as our surrogates. I'm not going to explain much about what Gaussian processes are, but the main concept is that we're not parameterizing the actual function, we're parameterizing the correlation between your points. We're really telling what's the length scale in which the function typically varies. And we use that length scale as a hyperparameter when we're doing the training of the surrogate model, the Gaussian process. So let's go to applications. I'm going to drink some water. Let's talk about how we have used this technique to study 4 devices here. And let's start with the SPARC, because that was the first application of this technique. So we're working with Commonwealth fusion systems, and we want to predict high fidelity what's the performance of the SPARC plasmas without assuming quasi-linearity, without assuming that we have a gyrofluid turbulence. So we first studied the primary reference discharge, the PRD scenario, and that has been studied thoroughly. We have done empirical modeling, popcorns, we have done quasi-linear modeling with DIII-D. We have done also standalone gyrokinetic simulations locally, but we have never done that profile prediction directly with gyrokinetics. That's what we're trying to do here. So it's an inductive scenario, it's repeated, and we're assuming we'll have an MEH value. So we take the boundary condition, as the boundary condition, we take the ITER value, which is H mode operation. And so we included a lot of physics here. We included alpha heating, energy exchange, radiation from all your ions mix. We ran quite high fidelity gyrokinetic simulations, electromagnetic gyrokinetic species, full geometry, full collisions, and we were looking at iron scale turbulence because we know that it's going to be dominated by ITG, it's going to be mostly long wavelength turbulence. And we're doing multi-channel TE, TI, and ME simultaneously. We achieved this prediction with only 16 evaluations. That's why we can start doing this with portals, because instead of you needing hundreds of evaluations, with just 16, we can get converged solutions. And I'm showing you here electron temperature, ion temperature, electron density predictions directly with CGR of how it compares to quasi-linear DIII-D. We see here that DIII-D does pretty good at predicting temperatures. It misses the density peaking, and we're trying to understand why that is missed in the gyrofluid quasi-linear modeling. And the fusion gain that we predict for a scenario is Q of 8, which is within the scatter of all the different saturation rules that we have tested with DIII-D. Let me mention that Q of 8 is above burning plasma conditions, above even, of course, the core mission of SPARC, which remains to be Q greater than 2. And something else that we can do with this framework that is very nice is that when we obtained that converged set of profiles, we have information about how the fluxes are affected by those 6 free parameters that I was talking earlier. So what we can do now is to say, well, I'm going to change the input power that goes into SPARC. Instead of 11 megawatts, I'm going to test what happens at 25 megawatts at maximum power. And because we are reusing the previous training, we can get a new converged solution in just maybe 4 or 5 evaluations. Much cheaper. So that's what we did. We predicted SPARC profiles, electron temperature and electron density, with the 2 different input powers. And something to note here is that we have more than double the input power, but the temperature in the core has barely changed, maybe by like what, 3 kV in the center. And that's a signature of a stiff ITG transport, meaning that we're really at marginal stability, and any increase in the flux a lot will not increase the gradient much. We're in that stiff condition there. And that has a consequence. That has the consequence that the maximum achievable fusion gain in SPARC will be determined by how low power you can sustain H mode operation. Because we have assumed, here that the pedestal is fixed at the IPEL value, but at some point, if you reduce the power too much, it's going to back transition to L mode. That back transition power is very uncertain, so we don't know at the moment what's going to be. The error bars are big, even for the H to L. The L to H is this is the L to H, so the H to L is even more uncertain. So we don't know what's going to be the maximum Q achievable in a SPARC, but definitely it's going to be at the lowest power you can run H mode with.
Hey, Pablo, you have a comment in the chat.
All right.
You want to look at it, or do you want me to read it?
I can look at it. So Miliano Fabio asked if SAT1 has the same density picking of Ciaro. Actually, SAT2 seems to be very flat edge density profile. Actually, that's a good question. SAT2, I think, predicts a lower peaking than SAT1. I don't have the right now the exact numbers of how underpredicted the peaking is, but CGRO predicted the largest peaking of all TGLF saturation rules. And I think SAT1 got the closest. But I checked that for you, Emiliano, and you can take a look at my nuclear fusion paper. I have all the comparisons there. Thank you. So, something very nice to see in the predictions is that they actually are in very good agreement with global scaling of both density peaking and confinement time. So this is a database of JET ASDEC stack rate and CMOT density peaking versus collisionality points, and the Angioni scaling in magenta here. And with CGRO, we predict basically the same density peak. And we actually captured the trend of collisionality. So if we go back, you see that at higher temperature, at high power, we also get higher density peaking. That's because we're going to a lower collisionality regime. And that's actually what's seen here, that we get higher peaking when we go to lower collisionality. And the energy confinement time is also captured, so almost on spot. And we capture the power degradation. So when you go to 25 megawatts, you get lower confinement time. And that's consistent with the tau 98Y2, the scaling law. So this was a very nice check, very nice to see that we were matching the global scalings with these first principle simulations. All right, so that's SPARC. Let's talk about ITER. We wanted to do ITER predictions, the first ITER predictions directly with nonlinear gyrokinetics. I was quite excited to do. So we were interested in the baseline plasma that has been studied quite a lot with quasi-linear models. This is from Paula Mantica's paper with qualities, with TGLF. It's an inductive plasma, MBI-CH heated, and it's also an MEH mode. So we are assuming here again that we have a pedestal at the IPET prediction at the Philip ballooning boundary. And these are the results. These are the first predictions of kinetic profiles, multi-channel profile, nonlinear gyrokinetics ITER. We predict a fusion gain of 9.4 with almost 500 megawatts of power. And let me tell you that actually the scrape-off layer power is actually well above the L2H threshold, about 40% higher than that. And from the SPARC results, that means that actually we can reduce the input power from 53 megawatts to something lower, increase Q, and hopefully still remain in H1. Yes.
How is the LH threshold calculated?
This is the Martin scale.
Okay.
Yeah, with isotope correction. Yeah, so again, we use the technique of reusing the previous training data to modify the input power and get a new solution in just 5 or 6 iterations. And we reduced it to 29 megawatts. And you can see here, you almost cannot see any difference in the ion temperature profile. Again, that's signature of stiffness. You are not really increasing the fusion power much when you go from 29 megawatts to 53 megawatts. And that has the consequence of increasing your efficiency. We predicted a Q of 17, also at around 500 megawatts for ITER, if you can sustain that H mode there. So we find the same ITG, very stiff transport in ITER. And we did something else. We said, okay, also reducing the training data, we said, what would happen if we actually reduce the pedestal density? So we reduced the pedestal density to 75% of the value at fixed temperature of the pedestal, and that consider that that's a good proxy for the effect of RMPs on the pedestal for L suppression. So we reduce the density there for a new prediction of the temperatures, and we've got a fusion gain of 6 with that proxy for L suppress H. And again, let me emphasize that this has been the first time that we have a view of ITER directly, of ITER profiles directly with nonlinear gyrokinetics. That's very exciting. And Nathan is going to submit a paper on this soon. But okay, so those were predictions of future machines, SPARC and ITER, running plasmas. Let's use this Portals technique to study current experiments, to validate the models, to validate ion scale nonlinear gyrokinetics. So first example is JET. So I'm collaborating, I've been for a few years collaborating with Oak Ridge to do JET studies of the isotope effect using main ion charge exchange diagnostic, and it supports the modeling there. And all right, so a little bit about the experiments in this JET yet in the jet machine. So we're looking at isotope effect, meaning the observation that as you increase the isotope mass, you increase confinement. You can see this in this plot here, from hydrogen in red to the deuterium in blue, and pure tritium plasma that we run in jet in magenta here. You see a clear increase in energy confinement with higher mass, and that's actually inconsistent with naive Jeroboam kind of like thinking of how turbulence should behave. And the isotope effect has been studied in many different conditions, and these plasmas were ohmic plasmas, low power. Well, the only input power is ohmic heating here. And that actually means that we can avoid or remove some effects that we know affect the isotope scaling, such as the pedestal, the rotation, the flows, the high radiation. So these were quite vanilla ohmic shots, perfect to study the physics of core transport, of core turbulence. Something to note is that the power flows very strongly from one isotope to another because the ions are only heated by energy exchange. And the energy exchange with electrons depends inversely with the ion mass. So we're going to have a difference of factor of 3 between hydrogen and tritium in terms of how much power goes to the ions. So the starting hypothesis of why we have that increased confinement when we increase the mass. The starting hypothesis is the one from Philip Schneider a few years ago in Aztecs that observed and demonstrated with gyrokinetic simulations, standalone simulations, that the increase in power that goes through the ion, this is total power, sorry, the increase between the two isotopes in power can be accommodated by a very small change in the gradients because of how stiff transport is. That was the reason why you could get high confinement when you were changing the mass, because of how stiff ITG transport was in those conditions. So we did that first with the standalone simulations. These are still not portals, and we could not recover that stiffness. In JET, to recover the change in flux between tritium and hydrogen required almost a factor of 2 change in the gradient. That would not explain our observations in JET. However, there was a caveat, and this is the caveat that portals resolves, which is that when you're actually changing the gradient, you're actually changing many things from one plasma to another. If you're actually changing the edge gradient, that's going to affect the core gradient as well. So you have to do it self-consistently and multi-channel. And that's what we wanted to do. We took very high fidelity, nonlinear CR simulations. I'm not going to go into all the physics included here, except one of them that's going to be important for the next slides, which is that we're only modeling ion scale turbulence. So if this is the linear spectrum, this linear growth rate versus wave number, we're actually stopping at 1.5 theta-ergo I for each isotope. We ran those portal simulations, and these are the results. We observed that we are able to predict electron density, ion temperature, and electron temperature for the tritium plasma pretty well. Arguably within error bars, even for the ion temperature, slightly over-predicted, but not much. But as you decrease the ion mass to hydrogen, we start having a strong over-prediction of the ion temperature. And that meant that in our prediction, the trend of confinement was broken. We actually were predicting higher confinement in hydrogen versus deuterium with these nonlinear CR simulations. We could capture the trend with tritium. Tritium remained the highest confinement, but the other two were broken. And yeah, as you can see here clearly, the ion temperature predicted with our framework was much higher than the experiment in dashed line there. So, yes. So we have a suspicion. We are exploring why that's the case. If you're actually including so much physics in those simulations, why you're not able to capture the turbulence, why you're not able to capture the right transport levels. And as I said earlier, we're running ion scale simulations, and something interesting happens when you reduce the mass of your ions. When you go from tritium to deuterium to hydrogen, you start actually getting the electrons and ions closer together because the masses of hydrogen and electrons are closer than tritium to electrons. That means that in turbulence, electron ion scales start getting more closer together. Here in this linear spectral linear growth rate in wave number. Here you see a zooming region. You see that for the tritium, the ion-directed bands, the ITG and the trap electron modes that become CTG afterwards, it's much more, the transition is much sharper. Whereas when you go to hydrogen, the two start blending together. And that suggests that what's actually changing from one isotope to another is the cross-scale coupling between high K scales and low K scales. And that's actually consistent with Nathan's work a few years ago that suggested this as well. So we're currently exploring this option, this hypothesis. Preliminary results seem to suggest that actually that's true, that as you go to hydrogen, you get more cross-scale coupling, but we're trying to determine if that's enough to explain the overprediction. This is still ongoing work. We're probably going to publish this soon and keep that exploration in future studies. All right, so let's go to our last example. The study of multi-channel multi-field gyrokinetic validation in DIII-D. So we had dedicated experiments in DIII-D, either similar shaped plasmas that are a good target for multi-channel validation because they are as close as possible to ITER baseline plasma. This was a mixed MBI VCH heating with fairly low rotation, and was also an RMP unsuppressed MEH mode regime with a Q95 3.4 and that normalized beta. And the flux ratios, QI over QE over the entire plasma core was above 1. That meant that ion scale simulations are probably enough to capture all the behavior. And also linear CGR simulations also suggest that ITG dominates with some TM in outer radii. So this was a good target to use portals where, in which we are using actually ion scale gyrokinetics. And we did the flux matching of QI, QE, and gamma E. We achieved that residual, low residual at just 16 iterations, quite cheap. And these are the results. We're actually predicting the kinetic profiles within error bars. We're doing the electron temperature, ion temperature, and electron density. We're studying at RRA of 0.8, rho of 0.8. And from the final converged profiles, we actually calculated what would be the carbon density. So we calculated B and D from the simulation. And the gradients of carbon are also quite well matched, well in agreement with experimental measurements, even though, as you can see, it's quite scattered, but it's at least consistent with experimental measurements. But in DIII-D, we also had a lot of diagnostics measuring turbulence. So we wanted to compare how we were doing. And this is an example of beam emission spectroscopy, BES. We were measuring that at 2 locations. And we had, in the gyrokinetic simulation, very good agreement in the shape, in the actual intensity, in the amplitude, and the cross spaces, the radial trends were matching all those turbulence features. The CEC, which measures electron temperature fluctuations, whether you're actually matching or not, depends on the analysis technique of the experiment. So we're actually right now, this remains under investigation of what's the right way to model the CEC. But in any case, the shape of the spectrum is very well matched as well. So this is very nice because you're matching all the profiles, kinetic profiles, and your measurement of turbulence is also consistent with the simulation. We're also looking at impurity transport. Low Z, we're doing lithium and carbon, matched reasonably well with our gyrokinetic predictions in terms of the gradients. However, as you go to high Z, calcium, for example, you start having disagreement. This is an example of the diffusion coefficient and the convective velocity. And that's well above outside error bars. And this suggests 2 things. Either either you're missing physics in your high scale gyrokinetic simulations for the impurity transport, or you actually have inaccuracies in the inference method. And the way why we believe this is possible is because we have found that there is a charge dependency of the diffusion and convection coefficients. And when you're actually inferring calcium, in this case, calcium transport with from laser blow-up injection, you are assuming that you don't have the dependency, that D and B are equal for every charge state. So we believe that's a possible source of why this is not, this is why this is in disagreement. And so, something I want to mention is that for this validation study, doing multi-channel flux matching was actually required. So in this example here, I'm showing the diffusion coefficient for lithium, calculated from the profiles that we predicted in red. And what happens if instead of predicting profile, you're taking standalone simulations, locally matching QI, and doing the calculation of diffusion, you can get changes of like 30% in the core of the plasma. So it's very important that when you're studying, you're doing validation, you're actually trying to match as many channels as you can, because then that means that you're probably in the right turbulence regime that is representative from the experiment. All right, so those were the 4 examples that we have run this year. And let me talk about now about advantages and challenges of Portal. So first of all, why does Portal work so well? Why can you get convergence with just 15 to 20 evaluations? So we have here some advantages that probably explain why you're getting that speed up. One of them is that you're robust to marginality. So when you are looking at the heat flux versus gradient, when you get to marginal stability, you start with having no turbulence, and suddenly you start having a turbulence that grows a lot, and you want to get to your target. When you get to that marginal state, unless you run very long simulations, you have a lot of oscillations or a lot of error in that calculation. So you're using a numerical method that actually needs to calculate the numerical derivative around that point. That becomes messy. However, for us, that's not a problem because actually we can introduce the uncertainty of the simulation into the surrogate model so that we have a smoother behavior and we can get to that point much easier without needing to calculate the numerical derivative. Actually, also, we're not spending time in the stable region. If you have a method that calculates the derivative there, you're probably going to spend a lot of time until you get to the target, whereas here we're going where the action is happening very fast. And this optimization method is suitable for global optimization and multi-channel, and we don't need to tune for step sizes or the grid of the numerical Jacobian, things like that. This makes things easier than standard methods. But of course, this is not all perfect. There are some challenges that we're trying to overcome. For example, one of them is that if we are actually having a small training sets, maybe like 5 points to start the surrogate training, that may lead to bias optimization. You have to be very careful about how you select your training set. You don't want to avoid regions where the solution might be, where you're focusing too much locally. And that also makes it very sensitive to the range of gradients that you allow it to evolve. You say, I'm going to search for solutions within 50% of your experimental value. That's the solution is then you get is going to be sensitive to that choice. So you have to be careful. It's also difficult to train surrogates on eigenvalue solvers that present discontinuities. So this is an example from DIII-D here on the right. This is very zoomed in the gradient, but sometimes you see clear discontinuities because suddenly a mode becomes stable, and feeding that or handling that behavior is very hard. Trying to find solutions to how to make this more robust. Also, sometimes we observe hill-like behavior, meaning that the residual, we do not see any progress, and suddenly you get a lot of progress in just a few iterations. And even though it performs better than other methods, which are up here, they need much more to converge. Having this discontinuity there in the behavior is not desirable. We're trying to determine how to avoid that. And finally, there's no straightforward definition of converge. You have a direct modeling framework. You can tell that something is converged because you have run it so long that your gradients and profiles don't change much. And we don't have that here. You have to determine if something is converged from just looking at 15 to 20 evaluations, and that becomes tricky. And we're also developing methods to make that, create that metric more robust. So these are my conclusions. We developed a new tool that opens new pathways to predict performance in future reactors and also to study turbulence in current experiments. We have done a both validation study and prediction of future devices, very different from each other in terms of size. All that with first principle simulations. So And here's some of my conclusions. I'm not going to read them. We've looked at what we have found in those experiments. And here are some papers to move forward with and some talks that Nathan and I are giving. So yeah, I'm open to questions about it. Thank you.
So we could take questions from the room. Remote people should put your hand up and we'll monitor that. I see Martin has his hand up already.
Yeah, sure. Very nice talk, Pablo. I just wanted to get back to this question of density profiles. I noticed, I think it was on slide 40 or 41, the predicted profiles for ITER were very flat, very surprisingly flat. So is the density profile being modeled? And
yes, this is consistent with turbulence. Yes, and actually, this plasma had also pellets, so it's not like it's all driven by transport. So we are accounting for that, and we still get quite flat profiles.
I mean, that's somewhat different than what you had shown previously for SPARC, for example.
Yeah, I mean, the peaking may be somewhat similar to SPARC, but it's true that SPARC is like source free in terms of particles. You don't have MBI or pellets in those simulations. So we still have to compare these predicted peaking with empirical scaling. We haven't done that yet, but that's kind of like next step to see how different this is from what you expect from the scalings.
Okay. Yeah, I mean, and there's a lot of leverage there, so it's an important issue.
Yeah.
All right, thanks.
Thanks.
So Connor, you have your hand up.
Yeah, I was thinking about I was curious about your JET work where you're talking about extending to doing more multi-scale simulations, and I was wondering if there's any difficulty in portals to do those, or is it just, you need a stronger computer?
Yeah, it's a matter of the computational cost of each individual simulation. I don't think portals, it would be hard. We probably would get convergence again within 10 to 20 iterations. The problem is the cost. So each of those TLS simulations that I was showing, the cost of doing all the evaluations that already I hear that we're doing cost about 2 million CPU hours. A single local multi-scale simulation would be way more than that. So you have to be very careful. And I don't think we are ready to do full multi-scale with portals yet. It would be too expensive.
Okay, thank you.
So I had a question. In the SPARC simulations in the PopCon space, it looked like a lot of the space is at pretty low density, if I remember correctly.
In this part.
Yeah. And relatively low density.
Yeah, this will limit up there.
Right. So the concern is with strong ICRF heating and tungsten walls. Why are these not tungsten dominated discharges? And I don't think you've modeled that. But where is that? What do we think about that part of the space?
The problem with that is that we don't have predictive capabilities to know how much tungsten total we're going to have in the machine, right? So if we do predictions, even if we do that with portals evolving tungsten, which we are actually starting to do now, it will also depend on what value you give at the boundary condition, right? So it's going to depend really how much tungsten you expect to be in the plasma, and we don't have predictive capabilities from that. I believe from the standalone work that Nathan did not observe like strong tungsten peaking in the core, but that doesn't say anything about what's the total amount.
Well, we know we're very sensitive to very small quantities, even if it doesn't peak. Okay, let's see, Andrew Maris, you have your hand up.
Hi, Pablo, interesting talk. I was wondering if you could speak about the appropriateness of assuming an ELMI H mode for the SPARC and ITER cases. I saw for the ITER case, you also included, an example where you reduce the pedestal as if there's RMPs. But I was wondering how appropriate is this SPARC case with the ELMI H mode? Since I understand that it's trying to avoid elms and spark.
Yeah, that's a great question. So actually, it's very convenient that I have this plot up here. This is with TGLF, but in this example here, we're actually studying what happens if you have a degradation of the pedestal pressure, how that changes your fusion gain. It's very hard to predict what degradation of the pedestal you would get with mitigation or like techniques to try to get free or express scenarios. So it's very hard to determine what's that factor from the beam ballooning boundary. In SPARC, this is what we found with TGLF. We haven't done this with CGR yet, but it should be very similar given that we got a fusion gain of 8 with CGR for the full pedestal. So you would expect lower than that. And that's, unfortunately, we don't have much predictive capability to know what that degradation factor is.
I see. Thanks.
Yeah.
Yeah, just to follow on the question about the tungsten.
Maybe you come closer to one of the microphones, but I don't think people will hear you.
So just to follow up to the question about the tungsten accumulation, I know you mentioned in the calcium transport section on D3D that the charge over mass ratio variance due to the charge state changing in the calcium at outer radii points is a problem, presumably. I assume that would be even worse with the tungsten because it cycles through a huge number of charge states in something like SPARC. Are you guys implementing something to deal with that when you do the tungsten transport, or is it?
But actually, that's a very good point. We are not exploring right now options to deal with that. Very hard problem, probably requires more attention. What we have identified, so when I was talking about the calcium, I was talking more about the inference method when you want to validate with experiments. Actually, if you have tungsten injection with LBO, that would be even more difficult.
Okay, yeah.
But also, when you study that with gyrokinetics, to look at DFV, in principle, you could run and you could obtain DFV for each charge state, but that, of course, becomes very expensive. So you will have to identify key charge states to do it for.
Yeah, I mean, you do something like what Francesco did, right?
Like
you use a lump sort of impurity.
Yeah, purity model. Yeah, I mean, we haven't thought about that yet. But
Okay, yeah, I was just wondering because it seems like if you're having problems with calcium, tungsten is just going to be way worse.
yes.
Okay, Colin Roach.
Hi, thank you for a very fascinating talk. I was actually forwarded by Francis Casson forwarded the invite to this, so I hope I'm not crashing, but it's a fascinating talk. I just wanted to ask a question about your algorithm that you're using in portals. And my question I had was, you mentioned at one point that in your for one of the calculations, I think it was the first one you showed, was it SPARC?
Yeah.
You said you did 16 profile evaluations in your in the transport solution. I'm just wondering, I guess what the real killer is how many local turbulence simulations you have to do. So for each profile, how many flux evaluations are you doing? How many local gyrokinetic simulations are you doing?
Yeah, that's a great point. These 16 evaluations number that I've given, that's number of evaluations per radius. So this is not the total gyrokinetic simulation we have done. In this example for SPARC, we run with 4 radii because we observed from both experiment and from the TGLF simulations that the gradient profile really is very flat, very monotonic. We do not expect any really like fine grid details of the radius. So we run 4 flux tube. Now we are expanding to 5 when we are doing the ITER simulations and the JET simulations. We extended to 5 because we're doing a database analysis in Akator-Simon and observed that 5 actually reduces the error in the coarseness of the grid by significantly. So you get like very accurate when you compare to like fusion power that you get out of the plasma when you do like 5 radar points should be enough. So hope that answers your question.
Okay, so you've got 4 or 5 flux tubes across the radius.
Yes.
Yeah, but how many do you have to do many evaluations of those with a given temperature and density profiles with different gradients? Or do you just take the gradients that exist at that particular time slice or whatever?
Yes, so we only use the gradients at that specific profile. So really
And you-
the 16 number here, you multiply by 4, and that's
Right.
the total number truly of the gyrokinetic simulations we have run to get that.
Okay, so it's tiny, and that gives you a very small training set or whatever to. Okay, thank you very much. It's fascinating. It's a very small number indeed. Thank you.
Yeah, so great work. And I just wanted to comment the way I always do, that the H mode test, so we don't understand the turbulent transport yet.
Yeah.
And we expect, of course, an order of magnitude larger turbulent transport in, say, ITER and SPARC, because of the inverse 1 over rho star scaling, the inverse scaling with rho star squared of transport that's predicted anyway. So, I mean, things are very sensitive to the pedestal as you've shown, and I think you could fall into the same trap that people fell into when they tried to say ITER wouldn't work back in the 90s by not knowing what the H mode pedestal would be doing. So that's something, of course, we have to address as a field, right?
Yeah, no, that's for sure. It's very important that assumption of the pedestal has been taken in this work completely as a given, with some ad hoc parameters that you saw, ad hoc degradation from the boundary. But yeah, I agree with you that that's a big issue. And as I said, like really what's going to determine the maximum power, the maximum fusion gain in both SPARC and ITER would be, how you can sustain that pedestal. So I do agree with you there.
Yeah, and the other comment I wanted to make was, I think I mentioned this last time you presented on the jet isotope effect, is that I had actually looked into this based on Nathan's mass ratio scans in 2015, his 2015 paper, and you can infer an isotope effect from that. And it's interesting that it's an unfavorable effect in the ion channel. You get a mass ratio scale or a mass scaling of 0.28 for the ions, and it's unfavorable, but the electron channel is favorable, and you get a mass scaling of exponent of 0.44.
Do you have a publication of that you can send me? That's
It's just just taking what Nathan did and scaling it.
Okay.
As if it were an isotope effect. He varied the ion to electron mass ratio to look at convergence of multi-scale simulations for a different reason. But you can extract an isotope effect from that in the two channels. But we should talk about that more. I mean, that's anyway.
Let's follow up. Thanks, Dan.
Yeah, nice work. Though. Thanks.
Close to the hour, we'll take one more question from Francis Casson.
Thank you. Yeah, very, very nice talk. I'm interested in the number of dimensions you have in the surrogate. I think you said that there were 6, but I guess when you're exploring only 15 evaluations, the dimensions that you're really exploring are the temperature gradient drives, and the sensitivity to the other parameters is quite limited in the space that you explore within one simulation. Would that be the correct assumption?
Yes, actually, that's a very important point. That something that I've implemented to improve the convergence even further is that at the beginning of the training, like when we have like 5 to 10 points only, I only fit into the gradients, the drivers. And then after that, to refine the solution, I start adding the extra dimensions of the temperature ratios and collisionality. Because when you start getting very close to your final solution, things can become sensitive. So I was adding those dimensions afterwards, but that's a great point.
And a follow-up is, do you have an independent surrogate model for each radius, or do they inform each other?
No, totally independent. They are local simulations. They're by construction already independent from each other. So yeah, the surrogates are independent. And actually, I'm fitting surrogates independently to turbulence, to neoclassical transport, to turbulent exchange. So I'm separating all those fluxes, putting surrogate models individually to each of those at each radius, and then putting everything together into a residual metric. Yeah, thank you, Francis, for coming.
Okay, well, let's thank Pablo again.